Start recording. Okay, so hello, today is October 1st, 2020. This is our fifth in a series of QEEG talks for CE recertification. And today we have Dr. Marco Congedo, who is a research director at the National Center for Scientific Research in France at the University Grenoble-Alpes. He is one of Joel Lubar's students, proteges, and did his dissertation actually many years ago under Joel on Loretta neurofeedback. And okay, so now I'd like to turn it over to Dr. Congedo.
Thank you very much, and hello everybody. So I was in Tennessee, Knoxville, with Dr. Lubar, working on neurofeedback. My PhD thesis was on the first neurofeedback system based on an inverse solution, Loretta, at the time, that I'm sure you have heard about. So at the time it was just starting, and we decided with Dr. Lubar to study this, and then I have kept working on improving the neurofeedback methods. And I've been studying methods for EEG analysis as well, and I'm lately working with a lot of brain-computer interfaces, which is very close to neurofeedback actually. And today I would like to introduce what we call spatial filters, so method for filtering the data in order to increase the signal-to-noise ratio and to analyze the data, but also those methods could be used and can be used, we actually did it already, to improve the neurofeedback signal that is fed back to the patient or to the subject that is participating to an experiment. So the aim of my talk is actually to introduce you to the machinery that is behind all those things, which implies that we are going to do a little bit of maths, but more on an intuitive ground, so helping the explanations with the graphical explanations. And so my aim is actually to introduce those concepts in an intuitive way, but still to give you an insight of what actually is going on under the hood, because if we understand what is going on, maybe we can see that it is not actually that complicated, and we can really study those things to really take advantage of those methods for our purpose. Okay, so let's start. The first thing to understand when we work with EEG are the simple and very widespread concepts of mean. Everybody knows the arithmetic mean, which is just the sum of some numbers, okay, divided by the numbers. So, for example, the mean of 2 and 3 is 2 plus 3, 5, divided by 2, because there are two numbers, and it is 2.5. So everybody knows that. And a little bit more complex is the concept of variance, which is how much those numbers spread around the mean. So the mean is what we call a measure of central tendency of a distribution of numbers, whereas the variance is called the measure of dispersion, how much those numbers are dispersed around the mean. So in order to estimate this dispersion, the variance just takes the sum of the squares of the dispersion, which is the distance between every number and the mean. So we take the squares because this distance can be positive and negative. So when we take the squares, it becomes always positive. And then we divide by the number again in order to have a mean of this dispersion. So this is the variance. Okay, those are pretty much very well-known concepts, but yet fundamental. So everything is based on those quantity, but there is a third quantity which is much less known, although it's very, very important. Before to introduce that, let me just tell that when we work with time series, which is the case of EEG, so EEG is a time series, so we have a number of samples, which are numbers, so a distribution of numbers, but they are sequential in time, so we call it time series. And usually, actually always, the data is bandpass filtered in whatever bandpass region of interest. And when we apply bandpass filtering, actually we remove the mean. So the mean becomes 0, okay? So in this case, the mean is 0 and the variance is simply the sum of the squares of the numbers, because the squares minus 0 is the sum of the squares. So it's just the sum of the squares of this number. And this is called also the energy of the signal. And it's also called the power, because the well-known power is nothing more than this. In the time domain is nothing more than this, the sum of the squares of the signal. So the more the waves are far away from 0, the higher the power or the energy or the variance. So those three names in this situation means exactly the same thing. Okay? So I was saying that there is a third concept which is very important but much less known, which is the concept of covariance, and that is the joint energy of two time series. So instead of taking the squares of one time series, we take the product of one sample of one series with the other, and we sum those two products, the products of those two samples for all samples. Again, we divide by the number of samples. And these covariance actually tell us how much those two signals tends to go together. Okay, so when one goes up, the other also goes up, and when the other goes down, when one goes down, the other also goes down. If they do like this, so they co-vary, then the covariance will be high. If they don't, if every signal does something different, then they do not co-vary much. So this number will be small. Now, actually, you know what the covariance is, because the correlation, which is a concept that is very much well known, the correlation is a covariance which has been standardized by the standard deviation, which is the square root of the variance of the two series. So this is the formula that you see on the bottom. I don't know if you see my cursor. I guess yes. So the formula on the bottom is this. We have the covariance between the two time series, x and y, divided by the product of the standard deviation of x and y, which are the square root of the variance of x and y. Okay, so this is the correlation. So covariance is nothing more than a correlation which has not been standardized. So whereas correlation is always between -1 and 1, the covariance can grow indefinitely. Okay, so this is the only difference. It's a non-standardized correlation. Now, let's recap a little bit what correlation is. When you have two time series, like in this example, okay, so you have two series of number. If you now plot those number on a Cartesian plane, okay, one series on the x-axis and one series of the y-axis, if you plot those two numbers, okay, those two samples, then you can have those kind of situation. So if the point with coordinate x and y, which are the two time series, scatter in this way, like making a kind of a circle, okay, then we say that there is no correlation. If instead they are aligned on one single line like this, then we have perfect correlation, because indeed when one series go up on the x-axis, then the other on the y-axis also go up, and when one goes down, then the other also goes down. So you see that in this case there is perfect correlation, but in practice what we do observe with empirical data, we never have zero correlation or perfect correlation. We have something in between. So we have, for example, in this case, correlation 0.8. So in this case, the points scatter around like in an ellipse in general, like in this way. When there is an ellipse in this way, then there is some correlation, but this correlation is not perfect. And the correlation actually measures the amount of covariation, okay? And it could be also negative. It is negative if when one series tends to go up, the other tends to go down, and vice versa, okay? So just keep in mind this, and reminds that correlation is always one if the points are on a line, as long as the line is not parallel to one of the two axes, okay? Because if they are parallel on one of the two axes, that means that if you know the value of, in this case, for example, if you know the value of x, you cannot tell anything about the value of y, because the value on y is always the same. So actually you cannot tell anything. So there is not actually correlation. But if the line is not parallel to any of the axes, whatever is the slope, then we have correlation. And the same goes for the ellipses. So just for recap, we have no correlation if the cloud of the points makes circles, where it doesn't matter where they are. There is no correlation if they make ellipses, but those ellipses are parallel. I mean, the main axis of the ellipses is parallel to one of the two axes, okay? There is correlation if they make kind of an ellipsis, and this ellipsis has a slope, which is, okay, not parallel to one of the axes. So this is to recap the concept of correlation that I think everybody knows already, but this really gives a clear picture of what's going on. Okay, the next thing we need to understand a little bit is some simple facts about matrices. So what are matrices? Matrices are just tables of numbers, just like in your Excel table, okay? You have certain numbers in a table, a certain number of rows, and a certain number of columns. And that is a matrix, that which we usually indicate with a capital letter, bold or not, but usually with a capital letter. That is a matrix. Whereas one single column or one single row of a matrix is what we call the vector. And actually one time series is a vector, okay? So for example, the first row of this matrix could be one time series of NIGI data. We are going to see that. So we need to understand a few operations that are very basics on matrices. The first operation is the matrix transposition, which is indicated by T. And matrix transposition is very simple. You replace the columns by the rows. So you take the columns, they becomes the rows, and the rows becomes the columns. Okay, so you see here, the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. So you transpose the matrix. And when you do that, then there are some simple facts about transposition, which are summarized here. That is, if you transpose a matrix that has been already transposed, then you come back to the original matrix. Okay, so that is clear. The row becomes the column, and then the columns becomes the rows. So you go back to where you were at the beginning. And then if you want to transpose the product of two matrices, like A times B, so this is a product of two matrices. If we don't put any sign in between two matrices, we assume that we are talking about the product, okay? Otherwise, you will see a sign like a plus sign or a minus sign, etc. So if there is nothing, it's a multiplication. So A times B, if you want to transpose the product, there is a rule to do that. It's simple. You just invert the order of the matrix and transpose all of them, okay? So A times B transpose is B transpose times A transpose. So this is something that if you want to, when you go back, and if you want to revise what we're going to say, is an operation that we are going to use. That's why I've been talking about it. All right, so an important class of matrices is actually what we call the diagonal matrices. Diagonal matrices are matrices where all the numbers are zero, except the numbers that are on the main diagonal, okay? Those are non-zeros. All the others are zeros. So those are called diagonal matrices. And diagonal matrices are very nice because it's very simple to make any kind of functions of matrices. For example, if you want to take the square of a matrix, if it is diagonal, it suffices to take the square of all the elements that are on diagonal. So now we are back basically to regular algebra, but we do it element by element. This is true only for diagonal matrices, not for regular matrices. So that's why diagonal matrices are very handy. So in the same, this is true for all kinds of functions. So if we want to take the square root of a diagonal matrices, we will take the square root of all the elements. If we want to invert a diagonal matrix, we just invert all the elements and so on and so on and so on. So it's very simple to work with those matrices. And also it's very simple to see what the product in this case does. because if you pre-multiply a matrix X by a diagonal matrices, then you simply give some weights to the rows. So the first element of the diagonal matrix becomes a weight that you give to the first row. For example, the first time series. We are going to use this operation again. That's why I'm talking about that. The second element of the diagonal matrix, multiply all the second time series. So just a scaling factor or a weight, whatever you want to call it. The third, multiply all the elements of the third series. So again, it's just a scaling factor. Okay, so this is what diagonal matrix does when it multiplies a regular matrix. I mean, an ordinary matrix. And among all diagonal matrices, the most important is what we call the identity matrix, which is the diagonal matrix where all the elements in diagonal are actually equal to 1. Okay, this is very important because this matrix is actually the equivalent in regular algebra of the number 1, because if you multiply the identity matrix for any matrix, I mean, with the sides must be compatible, but let's say, in this case, 3 by 3 matrices, then it does nothing. Just like the number 1, when you multiply with whatever number, it does nothing. And the same is for the identity matrix. It does nothing. It doesn't matter if you multiply on the left or on the right. It always do nothing. Okay? So doesn't change the result. So the result is always the same. So this is the equivalent of the number 1 in regular algebra. So in linear algebra, we have the identity matrix, which is the equivalent of the number 1. Very good. So I think so far so good. So there are a more few operations that we need to use in the sequel, and one is matrix inversion. You know, in regular algebra, when you want to invert a number, okay, 1/2 is 0.5. You can also invert matrices, and those matrices are defined in such a way that if it exists, is a matrix such that when you take the invert of the matrix and you multiply the matrix, then you get the identity, which is basically say that 1/2, for example, multiplied by 2 gives 1. Okay, so it's actually this the definition even in algebra of the inversion of a number. The inversion of the number is a number that multiplied by the number gives me 1. And so this is the case also for ordinary matrices. And also in this case, it does not matter if the multiplication is done on the left or on the right. And the other thing that we need to know is another class of matrices, which is called orthogonal matrices. Orthogonal matrices do not have a counterpart in regular algebra. So this is a concept which is a little bit more difficult to grasp. But in any case, those matrices have a definition which is very clear. Those are the only matrices for which when you multiply a matrix by its transpose or by its inverse, you always have the identity. Okay, so we have seen that this is the case for the inversion of the matrices, but this is not the case in general for when you transpose just the matrix. But for orthogonal matrices, this is the case. Now, an intuitive thing to understand is that if you apply an orthogonal matrix to a vector, so a vector would be 1 time series, the recording in 1 electron. But if you have only 2 numbers, then you can plot it this way. If you apply an orthogonal matrix to a vector, actually what you're going to do is you're going to rotate this vector. So this is a concept a little bit obscure by now, but it is going to become clear later on. Just keep in mind that an orthogonal matrix will rotate vectors. Okay, so having said so, now we can start talking about EEG. And what is EEG? Well, EEG data is a matrix. Okay, so every sample is a number, which could be positive or negative. And you have a certain number of rows. If we arrange the data in this way, the rows will be, every row will be 1 time series, 1 electrode. And there are a certain number of electrodes. Okay, so a certain number of rows. So this is a matrix of dimensions n by t, where n is the number of electrodes and t is the number of samples. In this case, in this image, we have 4 cycles, but could be much larger than that. In any case, it's going to be a matrix. Okay. And so remember, we have been talking about the variance and the covariance, and actually it turns out that if you consider this matrix C, which has on the diagonal, all the variances of each time series. So the energy of each time series is on the diagonals, okay? And the off-diagonal elements, the elements that are here, are all the pairwise 2 by 2 covariance between every two pair, okay? So the first with the second, the first with the third, etc., will be those numbers here, etc., etc. If you fill this matrix, this is called the covariance matrix. It is a very important object, this is what we are going to use all the time. But actually, it's very simple to compute. Just take your data, multiply by its transpose, and divide by the number of samples. This is actually, this is how linear algebra is so nice. Such a simple operation actually gives you this matrix that holds all the relevant information on what's going on with this data. Okay, we have all the variances and all the covariances. Good. And now we need a theorem that is going to be used all along in the sequel, which is very important and is called the eigendecomposition, or it's also called the eigenvalue and eigenvector decomposition, but is known also as the spectral theorem. This theorem says that a matrix like this, okay, such a matrix, which is a matrix that holds all the variances and the covariances, can actually decompose as the product of three matrices. So a matrix U, which is an orthogonal matrix, okay, I talked about that before, and the matrix sigma, which is a diagonal matrix, so we saw that as well, and then the matrix U transpose. Okay, now you don't see why this is important, but later on you will see why this is important. So basically we can decompose any of such matrix, always decompose as the product of an orthogonal matrix, a diagonal matrix, and the orthogonal matrix transposed. Good. So now let's make an example of what's going on here. So suppose we have only two electrodes. So you're going to have two time series like this. You can have like 1 second, 3 seconds, 4 seconds, 10 seconds, doesn't matter. You have certain number here and some numbers here. And then you compute the covariance matrix. We have said it's very simple. You take matrix E, X, you multiply by its transpose, you divide by the number of samples, then you get this matrix C. And then we have seen that this matrix has a decomposition of this kind. So suppose now this is the raw data. So we have two samples, two electrodes, sorry. So if we plot those pairs, okay, on the X and Y, so this would be X and this would be Y. So we plot all those samples like point in a two-dimensional Cartesian plane. So in general, EEG data, when you take a couple of electrons, is correlated, okay? And this actually, it is more, the more the electrons are close on the scalp, the more the data is actually correlated. And if they are very close, they are very correlated, sometimes even 0.9 or 0.95. So they are extremely correlated. So in general, you will observe actually something like that. So there is correlation between those two electrodes. And now, if you apply the matrix U of the decomposition, so this orthogonal matrix, remember, this is a rotation. In what sense is a rotation? Actually, what we are going to do is to rotate the axis, which are the axis of the plot. And now, if you lean your head, you will see that now the ellipse is actually the major axis of the ellipse is actually parallel to the x-axis. So if you remember, that means that now there is no more correlation. So this is called the principal component analysis, and you have probably heard about it. So this is the first signal processing method we are going to talk today. It's very simple. You just decompose the covariance matrix of the data. You take this matrix U, which is called the eigenvector matrices, and then you make this multiplication, and all of a sudden you have decorrelate the data. And when you have done this, you can do a little bit more, and you can actually apply a diagonal matrix, which is actually this sigma matrix here, which are the eigenvalues of the covariance matrix. So everything is given by this eigenvalue eigenvector decomposition. All we need is here, okay? So if we now take those, remember this is diagonal matrix, and we can apply any function. So this -1/2 means this is the square root of the inverse. Okay, so this is just a convenient way to write square root of the inverse. So basically, you take the diagonal elements, you invert them, you take the square root, and now you apply this multiplication before everything else. Now you do not only decorrelate the data, but we also make the variance of the resulting time series equal, and actually equal to 1. And that's why this is called a whitening transformation. So to recap this, we have seen that whenever you have a matrix of data, it suffices to compute the covariance matrix, decompose them by means of the eigenvalue-eigenvector decomposition, and then you can do principal component analysis, which is very much used, and you can do whitening, which is actually very useful because this whitening is always or almost always the first step that is performed to perform advanced signal processing methods. So advanced signal processing methods requires usually this step first, and then there is a second step to do to obtain your results. So we are half the way to get some results here, okay, of advanced signal processing method. So half the way is just doing this whitening, and this whitening is very simple. You just multiply the data by this matrix U, which is our eigenvectors given by the decomposition, and the square root of the inverse of this matrix, diagonal matrix sigma, which are the eigenvalue of your covariance matrix. So now let's see what this means graphically. So suppose this is the data, and this is the covariance matrix. So now here on the diagonal, so this is a heat map, which means that white is 0, a blue color is a negative number, and the red color is a positive number. Okay, so now we code each number of the matrix by color. So the darker the color, the higher the number. Okay, so this is a graphical way to see what's going on with the matrix. Okay, so on the diagonal we have the variances, remember, and all those diagonal elements are the covariances between time series. So in this case we have like 19 electrodes. Okay, so we have a 19 by 19 covariance matrix, and when we do the whitening, as we have seen, so we obtain, so if we take those two, we multiply, we obtain a new matrix. Now we apply this transformation, we obtain new data, okay, and now we compute the covariance matrix of this new data. Then the covariance matrix will be the identity matrix. Why? Because now the variance of all the new time series is actually 1, and the data is uncorrelated, so you have 0 covariance everywhere. So everywhere you have 0, but in the diagonal elements, which are 1. So this is the identity matrix. We have talked about that. And this is what the whitening does. So if you want to see what this actually looks like when you apply to EEG, this is what it looks like. So this is EEG, real data, with its covariance matrix, and this is whitening data. So data that is being transformed by this transformation, which is the whitening transformation. That's why I call it W. And with its covariance matrix, which is the identity matrix. Now, this data, whitening data, is completely meaningless. I mean, the whitening by itself does not do anything for us. However, remember, this is the first step to apply advanced signal processing method. So we need to go through this step, but we don't need to visualize the data, okay? And then we need to do a second step to really get to the point. So we are half the way down, okay? Good. So one thing to notice is that once we have applied the whitening, we obtain spherical data, okay? Data that is distributed in a spherical way, this way, okay? So now if you apply a further rotation to this data, whitened data, if you apply another orthogonal matrix, V I call it now, so it's a new one, and whatever it is, this is going to be another rotation of the axis, but still, you will still get a sphere around it, so still the data will be uncorrelated, and still the variance will be 1 for all the axes. So what this means that once you have done a whitening, you can apply any further rotation and you will not destroy the whitening. So this further rotation is actually the second part of the methods. Okay, so the first part is W, is the matrix W, and the second part is the matrix V. So then our advanced method will be given by multiplying the data by the product of two matrices, of which one is a whitening matrix, another one is a further rotation. And this is going to get us to some results. So let me give you an example, which is the common spatial pattern. I mean, you can call it in several ways. There are many algorithms that work in this way. In any case, the step one, as I told you, is the whitening step. So this will whiten the data. So the transformed covariance matrix will be the identity matrix. And then the second step will be, we take this data and now we apply a matrix V to a second matrix, and this will actually diagonalize this matrix as well. Okay, so by the end, as I told you, since when we apply a rotation to a matrix that is being whitened, we always keep the whitening, so we always keep the identity at the end, but this new matrix will always be diagonalized, because this is what V is going to do. It's going to be a diagonal matrix, and actually when we get this result with a good choice of this additional matrix to be diagonalized, that's why these methods are called the joint diagonalization methods, then we obtain some results. So this is all we need to do for performing a lot of different methods, and every different method depends on the choice of the other matrix to be diagonalized. Okay, so let's see some examples. But before I do that, let me also tell you that what you know as independent component analysis actually is an example, because independent component analysis can also be solved by this kind of methods. Okay, so independent component analysis is actually a set of methods that belongs to a larger family, which is called blind source separation. And the idea of blind source separation is to separate the sources of EG in a blind fashion, meaning that you do not assume knowledge of where the sources are or what they are, and you do not assume any knowledge of what the medium of propagation of the signal is. So in the brain, there are some generators, which are some dipoles, which are actually physiologically are part of the cortex of the brain, and those electrical dipoles emit some signal, and on the electrodes you actually measure a mixture of all those signals, which is represented here. For example, the green dipole will affect all the electrodes, you see, and that's why all the data at different electrodes are actually correlated, because every electrodes hold some information of different generators. So there is something in common in the data of all the electrodes, and that's why they are very correlated. So we say that we have some sensor measurements, so our data, what we observe from EEG, but there are some latent sources S that we do not know at all, and what we want to do is to actually estimate those sources as given the data. Okay, so we have a model for this. The model says that this, what we observe, is actually a mixture of the sources, and this mixture is given just by matrix multiplication. We call it A. This is called a mixing matrix, and we do not know this matrix as well. So this is kind of magic. What we want to do, we want to estimate S without knowing neither X nor A. So we want to estimate S without knowing anything. Sorry, you know X, but you don't know A, and you want to estimate S. So this is very difficult to do. What we want to do to actually perform this operation is to find the inverse of the matrix A, which we call B, such that then we can, just by algebra, obtain an estimation of the sources, multiplying our data by a matrix. So this matrix B, as I told you before, is going to be the product of two matrices, of which one is a whitening matrix and the second is another orthogonal matrix. So in an intuitive ground, it's just like we observe a salad. Okay, so EEG is just like a salad. Everything is mixed up together. And what we want to do is to decompose this salad in such a way to be able to find all the ingredients. Okay, so if we can find all the ingredients, then we can either remove some of them, for example, for artifact rejection, or study just one ingredient. For example, for neurofeedback, I'm going to talk to you about those things. So let's see an example for artifact rejection. So here you have some, on top you have some data, some 6 seconds or so of data recorded on standard 19 electrodes placed according to the 1020 system. And in this data there are the blinks, okay, so the famous blinks. So those are artifacts. If you now decompose the signal by Blantzur separation, so you estimate the sources applying a matrix B, then you obtain something like this. So those are the ingredients of our EEG, basically. So those are the dipoles in the brain, I mean the activity of the dipoles in the brain that are mixed together to give us the EEG recording. So here the mixing is very clear. Notice how those artifacts are present basically to many electrodes. You see, even here, even in central electrodes, you can still see those deflections, and even in parietal electrodes, you can still see those deflections. So the blinks mix together with almost all electrodes, okay? And here, the blinks are isolated as the first source, okay? The blinks is only in the phase source, but is not elsewhere. So once we do that, now we can remove this source and we can reconstruct the signal. And this would be one way to de-artifact the data, okay? So this is gonna be now the most difficult slide of the whole talk. And after this, you can basically relax. So just hold on for the next 2 minutes. And hold well, because you're going to see some equations, but actually everything has been already been said. Okay, and now what I'm going to do is I'm going to actually show you step by step what we need to do to get something like this, to get this matrix B. Okay, to get this matrix B so that you can actually decompose your data and actually remove some components or study some specific components. This is something I'm going to show you later on. So remember, we want to estimate this matrix B. Once we have it, we do the product and we got our sources, okay? So how we do that? There are many methods, but one of these is very simple. So here you have some data. To make it simple, just 2 electrodes. So again, we compute the covariance matrix. We have already seen that. And remember, we compute the eigenvalue eigenvector decomposition, okay? And we compute this whitening matrix. It's just like before, just we have done so far. So once we have done, we have the whitening data. Why now is the whitening data? We have seen this before. This is the first step, okay? So once we have done that, the data is now uncorrelated and has unit variance everywhere. Okay, good. So now let's do the second step. In order to do that, we consider this called auto correlation matrix. So this is our whitening data multiplied by the same data but shifted in time. So actually here I'm graphically represented what that means. So here you have some data, and here you have the same data with the lag, this lag which is given by the Greek lecture tau. Okay, you see those samples are like those samples. So we are just shifting a little bit the data, nothing special, shifting a little bit the data. So we compute again the covariance matrix. Okay, it's the same thing as here, but now we have to actually add the transpose of this, because this matrix is not symmetrical, but that's a detail, so forget about that. So we compute the covariance matrix now of this, and now, simple, we do the eigenvalue eigenvector decomposition of this new covariance matrix, and we take the matrix V, and this is actually the second matrix we were looking for. Okay, so Blantzur separation is done by those steps. So now you know what it is. covariance matrix. You know what it is, eigenvalue eigenvector decomposition. You know what this W matrix is the whitening matrix, which is given by the eigenvalue eigenvector decomposition. You just apply this matrix to the data, then you shift the data and you compute some covariance matrix also. Then you need the second eigenvalue eigenvector decomposition to obtain this matrix V, and then you got your final results. So you see all this in the past 40 minutes, basically, to convince you that advanced signal processing methods are not actually that difficult. If I add more time, I could actually show you how we could do this with a language program like Julia or MATLAB or whatever in a couple of minutes, just writing like maybe 5 or 6 or 7 lines, actually. So it is not that complicated. And now you have actually, you know exactly what all the steps are to get to this point and to get this famous matrix B, which gives you the blind source separation or independent component analysis. Good. So what we can do with those kind of things? Well, we can do a lot of things. We can analyze the data. We can make particular studies. This is a particular study in which actually we had the chance to record EEG and at the same time with some subdural electrodes. We had 8 more channels from electrodes that are actually leaned on the secondary auditory cortex, okay? So under the scalp, just on the cortex, so they are at contact with the cortex, but not inside the cortex, okay? And so here we have the recording from one subject of those 8 electrodes, okay? So here is what we got. And here on the bottom, you have the blind source separation, so the source estimation obtained from EEG without using those intracranial electrodes at all, okay? So this is just your independent component analysis or blind source separation. So now what you have to notice that the first source that we have estimated is actually very similar to the intracranial recordings. And in fact, when we do apply an inverse solution like S Loretta or E Loretta to this source, because we can do that, then we have an estimation of where this source comes from in the brain. Then in this case, we used S Loretta, and then it tells us that it comes exactly from the left temporal lobe in a region that is very close to the secondary auditory cortex, which was where the electrodes are, okay? So blindly, without using the intracranial electrodes, we have obtained an estimation of the signal that is very close to what we could obtain by means of intracranial electrodes. So this is a demonstration, if you want, that blind source separation methods may actually be very powerful, and they can actually give you very valuable information of what is going on in the EEG. Okay, this is just one of many examples of what you can do with those kind of methods. Other things that you can do with those kind of methods is use them for brain-computer interface. You know, in a brain-computer interface, then you want to give the opportunity to a patient, for example, a paralyzed patient, to move a cursor on the screen, let's say left and right, just by imagining movement of the right or the left hand, okay? So when the patient imagines to move the right hand, the cursor will move on the right. And when the patient imagines to move the left hand, the cursor will move on the left. Well, how that works? Well, we again use those kind of methods, but now the second matrix will be different. The first matrix basically will be the matrix that has been the covariance matrix of the data that we have acquired while the subject has imagined to move the right hand. And the second one will be the covariance matrix of the data that has been acquired while the subject has done an imagination of the movement of the left hand. So we do some calibration, a calibration session. We ask the patient, okay, imagine to move the right hand. We record the data, we compute the covariance matrix, and then we say, okay, now imagine to move the left hand. We record the data, we compute the covariance matrix, and then again, this joint diagonalization that we have seen is going to give you the filter, the matrix B, that allows you to find the good sources that will allow you to now understand when the subject imagine a movement that you don't know what it is, if he or she is imagining to move the right hand or the left hand. Okay, so those methods are very useful also for motor imagery brain-computer interface, but they are also very useful also for studying event-related potentials. So you all know what an event-related potential is, okay? So this is an event-related potential that has been computed on the average of 80 trials, okay? And this is a P300 paradigm. So what we are looking for in this kind of experiment is this positivity, usually at central location. So this is the CZ electrode. So this positivity, it is actually the P300 we are looking for. However, we also have some early component, the so-called N100, the P200 component, which are visual. But for this data, we also have some residual blinks that when you average the data do not disappear. Okay, so in this case, the joint diagonalization of specific matrices again can give us these results, which is presented on the right. So this is the same data, but now has been filtered in such a way that the artifact has been removed. So again, without removing the P300 and without removing the N100 and P200 components. So you see everything else is intact, but we have removed the noise. So those methods are also used to analyze event-related potentials, and eventually, if you want, also to devise brain-computer interfaces based on event-related potential, which is something that we do in our laboratory. And finally, which is the most important, I think, for most of you, those methods can be used for neurofeedback. Okay, so this is very important. In what way? Well, remember that what we want to do by means of blind source separation is to decompose the signal, just like separating the ingredients of our salads. Okay, good. Now, when you do neurofeedback with one electrode, plus a reference, of course, then you have this electrode records something that comes from the brain underneath the electrodes, but it also records something that comes from the brain not underneath the electrode, elsewhere. So it records some signal, which is what you want to train. Let's say you put it on the motor cortex, for example, and you want to train the motor cortex. So the signal in this case would be what is produced by the motor cortex, but you will also record what we call interference, something else. The visual cortex or the motor cortex on the other side of the brain, etc., etc., etc. So when you do neurofeedback this way, then your neurofeedback signal is actually unspecific, spatially unspecific. You do not train the motor cortex, you basically train the whole brain, okay? Joel Huber used to say that all the time. Well, we train all the brain, we train all the brain. Indeed, and that's has some physiological reason, because these electrodes actually is sensitive to activity coming from several parts of the brain, not just underneath the brain. But now suppose instead of using one electrode, you use many electrodes, okay? And then you acquire EG from many electrodes, and then you decompose the signal. Then you can find some sources, and among those sources, you will look for one of them, which is what you're looking for, the signal, okay? And then you will actually ignore or remove or filter out, say it as you like, all the interference. So in this case, your signal would be much more specific, okay? And this, again, we can do very easily with the joint diagonalization method that I've been explaining in mathematical terms, which again boils down to simultaneously diagonalize two matrices. one of them will be whitened at the end, and the other will be just diagonalized, okay? But it's exactly the same, but we can also do those kind of things. And now I'm going to show you a demonstration of what you would get if you do such a thing for doing neurofeedback. So here we have some real data from a 16 years old ADD boy. And so these are 4 seconds of data. And this is the recording from the FZ electrode. And these oscillations that you see in the green ellipse are actually theta low alpha oscillation. Okay, so this is the spectrum in between 1 and 32 hertz, and you see the peak of the spectrum is about 7 hertz. Okay, so this is the typical EEG activity that we want to suppress in ADD patients. Okay, so we want to suppress this. Traditional neurofeedback would do that by placing one electrode at FZ, maybe in the bipolar settings, one at FZ and the other at CZ, and then filtering in the band pass around 7, for example, and then suppress this activity. But now, if you use blind source separation, these what you see on the right are the 17 source components that are estimated based on the original data. Okay, the first component corresponds to those theta oscillations. But what you should notice is that this component, the signal to noise ratio of this component, is much higher than in the original data. How I can tell that? Well, look the peak at 7 hertz as compared to the peak in the other frequency on the left, and now look at how high is the peak on the right as compared to the other. As you can tell, there is much more information at 7 hertz, only at 7 hertz on the right as compared to the left. So what that means is that this source component has much more signal to noise ratio. Why? Because implicitly we are suppressing all the other. Implicitly, if we base our neurofeedback signal, what we give back to the patient, only from the first source, we are implicitly ignoring all the others. Okay, so we are filtering out everything else and just give the signal based on this. So in practice, what would happen then when the subject do the neurofeedback? This now on bottom left is some EEG data of the same subject later on. Okay, and here now you have at FZ, you have some activity which is actually a mixture of theta and alpha activity. So you can see in the spectrum you have a peak at theta, but we also have a peak in alpha. Okay, and you can tell from the waveform that is not as clear as this. Okay, so it's a mixture of theta and alpha. So now if you were to base the neurofeedback on this signal, it could be ambiguous what you're going to train. Whereas this is now bottom right are the source estimated on this data, okay, in an unsupervised manner, okay, meaning that we don't need to estimate them online. This is just a filter that has been applied, but the filter has been estimated before. And now this is what actually the filter see. And what the filter see is only activity at the theta frequency band. Okay, so implicitly we are filtering out everything else, including some alpha activity that was picked up by this electrode. But now when we separate everything, we always keep the theta activity. So our feedback will be much more specific. Okay, so that was the end of my presentation, and I am now open to any question.
Okay, so thank you for that. Anyone have any questions? If you want to put them in the chat, or if you just want to unmute yourself, either one would work.
I don't see any chat in any case, but
Yeah, no, oh, we got something here. No, no. Nobody has a question? I think we have a special guest here today. Do I have that right?
who's this? Dr. Newber? Hey! Dr. Newber, please unmute you.
Yeah, yeah. Go ahead and unmute. Nope, you're still muted, Joel.
Click on the mic button,
I think
please.
I can do it. Unmute.
Oh,
Okay.
here we go.
There we go.
Yeah, I got in a little bit late because they gave me the wrong number. But anyway, let me ask you this question. The numbers that you put into the matrix, are they actually the raw values of either the current density or the raw values of the actual amplitudes that go into the matrix, the actual numbers?
In my examples at the very beginning?
Yeah, because I didn't see the first
No,
part.
those were just fake numbers, just.
No, but I mean, in reality, if you're actually going to use this, I mean, you put in current density numbers into either what's
Oh, no, this would be just what we record with EEG, so it would be voltage.
So it'd be all right. So it'd be the voltages. Okay.
Yeah, just whatever is your data that comes out from your EEG machine would be microvolts, right?
Yeah, so there'd be microvolts, not current densities. Okay, very good. That's great.
No, just microvolts. Yes,
Yeah.
regular EEG.
Good.
So what I'm understanding, obviously, here is that the more channels you have, you're saying you used 6 channels, right?
Well, in theory, I would use at least 12 to have a good decomposition, maybe even 16.
Okay.
That would be enough for most applications.
Mm-hmm.
But yes, I see this as a natural evolution of neurofeedback, which is even more promising than Loretta or S-Loretta neurofeedback, because it would be more precise.
Yes, of course. Yeah. All right. Good.
And we actually did some research on that. There are a couple of papers out. One with a group in Prague and one with a group in Melbourne. Actually, a student of Silberstein. And in both papers, we actually demonstrate nice results. So this method has been already tested. So it's not something experimental. Actually, it has been out for 3 years now, 4 years now.
And so you're saying that with this, I hear an echo. Oh, okay, it's just me. So you're saying with this that surface amplitude training, is that what you've mostly researched, or have you looked at further, more network, more of that kind of training?
Yeah, I mean, this is the traditional way of doing neurofeedback, which is nice, and but what I'm saying is that it is not optimal, and one can try to do better with that using the idea of spatial filters. And those spatial filters can be actually computed very simply, in a very simple way, just once at the beginning of the session, and then can be applied to the whole session. And then you don't need to do anything. I mean, everything else would be exactly the same. You just need an algorithm to estimate these filters at the beginning, and then you choose the source that you want to train based on scalp map, inverse solutions,
right.
Based on the power density. I mean, on the power spectrum. So someone that knows what he's doing would be clearly able to do that. And once you have that source, then you just say, okay, now train that source. And that would take care of artifacts, would take care of any kind of interference, and the training would be more specific. The price to pay is to have more electrons.
Right, right. And so the more you're also saying, I want to make sure I understand, you're also saying that you're using the more electrodes you use during the neurofeedback, not necessarily just for the assessment, the better, which would make sense.
Well, then you will need during your feedback, you will need a cap with, I would say, 16 electrodes, something like that. No more than that, because then when you put more, you start having other problems. So I would say 16 would be more than enough, or maybe even 8, depends on what you do. Something in between 8 and 16.
So right now, people are using 19 channel caps to do this kind of work. Are you saying what would be the problem with that? To try to think about?
No, there is no problem.
Oh no, for 19 it's
okay.
Okay.
So we did it for research purposes. So we have research software, but I don't think that, I'm not aware of any commercial software doing that.
19 channel Loretta? Yeah. Yeah.
No, Loretta, yes, but not spatial filters.
Oh, okay, yes, not spatial features. Yeah, filters. Yes. Yeah. Okay. Well,
so that's
we
that's
can
the reason why nobody else has tried, I guess.
Right. I understand. Okay. Now I understand the thing. We have a question here. Cher, do you want to read that?
Yes, I can. This question is from Ron. He says, Bob Thatcher argues that this kind of process distorts the time series and interferes with understanding network dynamics in terms of phase lag and phase lock. So are there areas where this is ICA is appropriate and others where the distortion in the time series interferes with the accuracy of the data?
Well, in this case, there is no problem, because what you want to do is to estimate one time series, which would be the source of interest. So whatever is the lag doesn't matter. There is no problem whatsoever, because all you want is one time series. And in any case, when we do neurofeedback, we do give feedback based in general. Of course, we can do other things, but 90% of the times neurofeedback is based on power. So on power estimates or amplitude estimates of the signal, and then we estimate this power with the sliding windows, and then we give feedback based on those estimates. And for those estimates, the phase is actually irrelevant. I mean, the estimates would be the same. Doesn't matter what is the phase, so that would not change anything. So in this case, there is no problem whatsoever. We can use those kind of methods without any problem. It's very simple to see. You just, if you take some signal, you compute the power. If you shift the signal a little bit, you compute the power, it's going to be the same. If you shift a little bit, it's going to be the same. I mean, the phase does not change the power estimate at all.
That's true.
So when you only need to estimate power, there is no problem. What Thatcher is saying is that when you do need to estimate now connectivity between electrodes, for example, then you may observe some distortion, because those connectivity measures are indeed based on phase. And then phase is a relevant parameter, and then you have to study what your method is doing to the original phase of your signal. But this is not the case of what we want to do now, because all we need to do is to estimate one time series, compute the power, and that would be completely irrelevant what the phase of this signal is. Irrelevant.
Mm-hmm. Makes sense.
Yeah, that makes sense. Yeah. Mm-hmm.
Do you have a question, Joel?
No, I said, I think people get all, so to speak, bent out of shape, because if you're dealing with connectivity, it is a problem to use ICA. We know that. We've proven that. Beyond that's well established. But if you're not using it for that purpose, if you're using it for what Marco's doing, or for what you're doing with the ERPs, no problem at all. It can be very useful. Here's an interesting thing. I liked your demonstration where you had the electrodes, the subdural or dural electrodes, and then you showed that you could estimate with the surface the same location. I think that's wonderful. So here's an interesting thought. What if you wanted to measure activity, let's say from a deep structure inside the brain, let's say from one of the basal ganglia or so forth. And we know that with Loretta now we can visualize that activity in these deeper structures with the boundary element method. So it'd be great, because it'd be a great way of cross-correlating the two. This is what we really need. You know, this is a big problem, is that you can see the red nucleus, we can see all these areas in the cerebellum. We don't have any electrodes on the cerebellum, but we can use these measures from fMRI to cross-validate that what we're doing is valid. So this is very important. And I think your technique could be used for that sort of thing. That's great.
Yeah, the problem remains how you correlate fMRI with EEG. So actually, there are some people sticking electrodes inside the brain for epileptic patients or stuff like that. That kind of data would be very interesting to analyze, to see if we can actually pick up this activity from the scalp electrodes using blind source separation or independent component analysis. That would be a nice proof again.
Wonderful.
Yeah, and beyond fMRI, you know, even SPECT and PET, and you know, to be able to correlate all of those, you know, imaging things. I have a technical question. So if you have the array on the cortex, does that artifact or interfere with the recording from the surface?
What do you mean array?
Well, if you have the cortex, you know, you're saying you can do this with surface EEG. What we're getting from, you know, the array that's on the
subdural electrodes. No, that does not interfere. Those are just plastic strips, transparent plastic strip, which do not interfere with very small electrodes that do not interfere with the signal.
I mean, you would
in a particular way, but they are actually small.
Yeah, you would think that it would somewhat attenuate it, but I mean, I know the scalp obviously attenuates, but you know.
Well, no, but that's just a very thin, transparent plastic. I mean, it's not regular plastic; it's like biocompatible plastic, but it's very thin, and the electrodes are very small. So no, that does not interfere with the EEG, which is actually, in any case, it's a macro signal. It comes from a large part of the cortex, so that's not. I don't think so.
Yeah. Okay, interesting. Cool.
Well, in any case, what I really would like to do next time we see each other would be to talk to you about my new field of study, which is called Riemannian geometry, and I wanted to talk to you about that since a long time, but I didn't have really an occasion so far, but I hope I will, because it's actually very interesting, and I think can be used for neurofeedback as well. So
can you give us a little preview? We have a few more minutes.
Yes, I can give you a little preview, because in my talk, the central object, which is the very important object, is the covariance matrix. So this covariance matrix actually holds all the information, statistical information of the signal, and the Riemannian geometry is just a metric to measure distances between those covariance matrices. Okay. So, for example, you in a natural and appropriate way. So it's just like a meter when you want to measure the distance, you know, between you and your husband or whatever. You use a meter like that. But if you use a regular Euclidean meter for covariance matrix, doesn't work, because the space in which those covariance matrices live is actually a curved space. It's not.
Okay.
Is not a linear space. So we need a different meter, but then simple, once you have this, then you can really measure distances between things. So what you can do is to say, okay, I define an ideal state of the brain. Like, I want the brain to be in that state. Okay, for example, Dr. Lubar, I don't know, for a patient, you pick up a moment where it's nice, or where you do not see any theta spindles or nothing. You say, okay, that's the brain when it's working properly. And now you estimate this covariance matrix. And now when you get new data, you just compute the distance and you give the feedback based just on this distance. So if you are close, you would suppress. And if you are far away, I mean, if you are close, you would, if you are close to this state, you would reward, okay? And when it goes far away, you say no, you don't reward. And then you would train the person to get close to this ideal state. And that would be actually very simple to do, very efficient in real time. And it's something that has not been done so far. So that could be something interesting to try.
That's interesting. But I know that Riemann, he fits what they call manifolds, which are curved surfaces to very complex, areas. And I don't know
it's called the Riemann manifold, yes.
Yeah, I'm not sure within the brain, how you construct the manifold between different areas. And
No, actually, it's just a mathematical concept. The manifold is just this curved space in which those covariance matrices live. Those covariance matrices do not live everywhere in the Euclidean space. They live only in a subspace. So because of that, you need a special way to measure distances, basically, because you have to take this into consideration. So because in those curved space, weird things happen. For example, in Euclidean space, if you have 2 points, there is only one line connecting them, right? One straight line, okay? I take like these 2 points, there is only one straight line connecting them, okay? And whenever I put 2 points, there will always be one straight line connecting them. Now consider a curved space, consider a sphere, okay? And take as one line the North Pole, one point the North Pole, and the other point the South Pole. Now, how many shortest line connect them?
It's not straight.
How many?
It's curved.
Yeah.
Infinite lines. All the meridians connect them. It's actually the same distance, right? So if you take 2 points anywhere on the sphere, there will be one line that has shortest distance. But if the points are at the opposite, okay, of the sphere, then there are infinite. So you see, weird things happen as long as you do not work in a flat space anymore. So you have to take those weird things into consideration. And when you do that, you have an appropriate meter. And when you have an appropriate meter, then you can treat your data appropriately. But that's simple to do, basically, and can be done in real time with very little calculations.
Okay.
Wow, that is quite a preview. I don't even know.
Well, I hope we'll have a chance to do that in person, because it would be much easier.
Yes, next year.
Maybe I will get big pleasure.
Yep. I mean, if Napa hasn't burned down by next year, we'll all be together.
I hope.
I don't think so.
Yes, I agree.
Yeah.
Good luck with that in any case.
Yeah. I mean, that's a great preview. I'm excited. I know that everyone, we're supposed to go to 9:30, but Marco, when we first came on, he said something has come up, and so he needed to end a few minutes early. So we're here at around the time that Marco needs to go. So any last questions? This is your last chance here. Okay, well, forever hold your peace.
Well, if you have questions, don't hesitate to write me by email. I will be glad to answer.
Yeah, and of course I have
no problem with that.
Yeah,
please don't hesitate. If you have questions, people just write, and I will try to answer everybody. Okay. And Dr. Luber, it was a pleasure to see
Yes.
you. I will invite you so we can Skype one of those days.
Okay, let's do that. Let's talk some more. Okay.
Yeah, that would be great.
Okay.
Thank you, Cinzia.
Thank you. Great to see you.
Thank you, everybody. Thank you, everybody. Bye-bye.
Bye.